if I put a capacitor and an inductor together, you know what that's called, right? Tank circuit. Very good. Okay, tank circuit. Now, if I pick my capacitor and my inductor very carefully, I can make it resonant. And you guys know resonance because he taught you about motors and capacitors, and he taught you that if you made them resonant, then the current and the voltage were as close to in phase as possible, and the circuit had as little resistance as possible, some kind of R in the circuit when you were all done. That was the smallest resistance at resonance, and thus it consumed the least amount of energy. And if it was outside of that, what happened to the motor? It heated, right? And if it heated, that means that part of the energy was turned into heat, and you lost it because it was useless, unless you're trying to heat the building or something. And if it heated enough, it burned the motor up, right? So you wanted to get it as close to resonance as possible. That was motor resonance. We're going to try and get our inductors and capacitors as close to resonance as possible for filtering. We're going to want to pass a certain frequency through, and we're going to want to reject everything else. Now, there's all kinds of filters in the world. There's some that pass high. There's some that pass low. There's some that pass a band. There's some that are notch, and they only pass a small little frequency, and so on. There's all kinds. And we'll build a few of the different ones, and we'll study as much of them as we can, but there are so many in the world that you're going to have to just, some of them you're going to have to visualize. You're not going to be able to build them. We're going to build what we can. We're going to build the interesting ones, okay? But again, we're doing the same thing, but we're interested in the frequencies that we're looking at in the circuit and doing something with the frequencies, not trying to make a rotational energy output maximized. Okay, the physical output. We're not trying to maximize a physical output. We're trying to maximize an electronic output, an electrical output. Remember, what's our basic rule? Controlling electrons, right? That's all we're doing. So we're trying to control some electrons that are vibrating a certain frequency. Now, you say to yourself, I know you're going to ask, what's a practical application? Okay, every time you tune a radio, you're doing that. All the radio signals are in the air at one time. When you tune across the dial, you hear this one, you hear that one, especially at night on AM. You ever do it on AM at night? And it goes, you know, there's like 1,000 frequencies out there, and you hear them all. They're all kind of jammed together. When you tune across, you're using this tank circuit right here to tune through the frequencies, and when you hit the radio station you want, that tank circuit passes that frequency through and rejects all the others. Because if you didn't have that there, it'd just be a big old jumble. And to be honest, if you take an amplifier that can actually amplify what's in the air, what do we call it? If it doesn't have this, it's noise.
White noise.
White noise. And that's basically all the stuff in the air that can be amplified. When I put a tank circuit on it, I can adjust it to pick just the one I want out of the air. That's not the only place, but that's one that's really obvious.